Science. We're in our 51st year of this symposium, and I'd like to just say thanks for coming on behalf of the College of Mines and Earth Sciences and also the College of Science. I'm Daryl Butt, the Dean of the College of Mines and Earth Sciences, and like to welcome you also on behalf of Dr. Henry White. Before I start and introduce our speaker tonight, I just had a couple of administrative things. Just so you're aware, our next lecture will be in March, and let's see, the date of that is, I believe it's March 8th, yeah, Thursday, March 8th, and our speaker will be Blythe McCarthy from the Smithsonian. Blythe is a conservation scientist, and she's been on assignment to the State Department trying to find ways to protect the treasures in the Middle East from being destroyed by the wars and the activities over there. So it's going to be a very interesting presentation. So mark your calendar. Our presenter tonight, Dr. Robert Hazen, I won't introduce, I'll let Dr. Turi Serling introduce him, but he's going to give a presentation on the story of Earth, and I suspect after his presentation you're going to also want to run out and buy his book, which also has exactly the same title, The Story of Earth. And so we're really happy to have him here, and what I'm going to do is turn the mic over to Dr. Serling, and Turi, you want to take over?
Yeah, it's my pleasure to introduce Robert Hazen for our talk tonight. I guess the backstory for me on it is that some years ago I was going to be going out in the field, and I needed to bring some books with me to read because we were going to be out in the field for a while, and it's nice to have something. And it's when you're away from University of Utah and your duties, that's when you finally get to read. And so his was one of the ones I picked up, and I read this book and I thought, wow, that is just a really fun way of thinking about things that I hadn't thought of, and I kind of wish I would have thought of that. So I thought when it came time to make nominations for speakers, his was one of the names that I put forward, thinking this is just really such a wonderful story. So Bob Hazen is from the northeast of our great country, and as a young man or young boy, I learned that he, became very, very interested in minerals and in music at the same time, and neither one really won out professionally. So he's been studying minerals his whole life, and he's been a professional trumpeter as well, and also interested in education. So he's at the Carnegie Institution of Washington. He's also a faculty member at George Mason University, and until last year he was also giving professional trumpet performances with various musical groups in the Washington, D.C. area. And so with that, I'm going to turn the mic over to him and allow him to tell his own story about the story of our planet.
Thank you. Thank you so much. We live on a planet of breathtaking beauty. Seen from the vantage point of our moon, we see that blue marble with the swirling white clouds. And it shows us that we live on a dynamic world, a world of change. So we look at this photograph and we say, is that the way Earth has always appeared? Has it changed over time? And if it has changed, how and why? So I want to explore this idea and tell you my conclusions right up front. First, Earth is transformed repeatedly over 4.567 billion years. And second is that life and rocks have co-evolved. You cannot understand Earth's great history without understanding both the living part and the geology, the rocks and minerals that support that life. And finally, I want to tell you something very exciting and very new that's driving my research today, and what I think is the most exciting new development. So we're going to look at this idea of big data and how big data can help us understand our planet's past and perhaps its present as well. Okay, So I want to first of all say that almost everything I'm telling you about tonight has been done by a group of brilliant early career scientists. Here's a few of the people I'll be talking about. You'll see some other photographs as we go through. And I really want to credit this. These are people who have backgrounds in all range of earth sciences, geobiology, paleontology, geochemistry, mineralogy, tectonics, but also in data science, which is a partner with us. And our data scientists at RPI have been incredibly important. And if you're interested in learning more about our work, I encourage you to go to our website, which is dtdi.carnegiescience.edu, where you can see some of the visualizations I'll be describing this evening, and also learn something more about our research. Okay, I want to look at a couple of really key aspects tonight and explore with you these ideas. The first one is called mineral evolution. It's the idea that minerals on Earth have changed systematically through time in a way we call mineral evolution. I also want to look at mineral network analysis. This is this new data-driven aspect of discovery, which is so fascinating and allows us to see mineral systems in a brand new way. Now, we're trying to do a few basic things. We want to document the change of Earth's mineralogy over the last 4 billion years plus. We want to try to understand how Earth compares with other planets and moons. So this is comparative planetology. And we certainly want to understand this co-evolving geosphere and biosphere. That's what's driving us. And everything we do in this reign relies on having data resources. When we're looking at the deep time change of Earth, we're looking at data that tells us about different periods of Earth's history. So briefly, I want to tell you about the data resources, the databases that are out there. One of the most important has to do with minerals. It's called rough.info/IMA. This is the largest mineral database that lists all the approved mineral species. And by a mineral species, I mean a unique combination of crystal structure, the atomic structure, and composition. And there are over 5,300 approved combinations, unique crystal structure, composition. So this database is amazing. It has compositional filters, it has structural filters, but what we've done is, over the last 8 years, added something called the evolution, the Mineral Evolution Database. Building databases is hard work. We have 130,000 records. We started with 0. This is done by what's called brute force. You go into the literature, you find a paper that describes a mineral locality. You open up the paper, you find the age. You find the minerals that are present at that locality. You find the techniques that were used, all the metadata, and you build this one record at a time. We use primarily undergraduates who have passed with high grades in the mineralogy class at University of Arizona. And over the last 8 years, we've built this from nothing to a very substantial database. I should tell you one other thing. The original database was, no big national funding agency supports these databases. So the Rough database was funded by a grant from Mike Scott, who is the founding CEO of Apple. He happens to be a passionate gem collector. He wanted to know all the different minerals that might turn into gems. And the one provision he said, I'll give you $5 million to start a database, but you have to name it after my cat. We don't like the idea of calling this rough data. It's actually pretty refined data, but it's that. There you have it. Okay. Now, the other big mineral database is quite different in its framing. This is mindat.org, and it's crowdsourced. It's crowdsourced by mineral collectors. So there's a platform, and you can get sort of approved to be one of the maintainers of this site. You go in, you type any one of 300,000 and growing number of mineral localities. Each locality has a list of minerals. There's now over 1 million mineral locality pairs. That's big data as far as mineralogy is concerned. So we have all that data. There's lots of other things we do. We have EarthChem, run by Kirsten Leonard out of Columbia. That's a database that has geochemical data, it has igneous petrology and other kinds of petrology data. Very fundamentally important, supported a lot by National Science Foundation. We have MacroStrat. Shannon Peters is the mind behind this at the University of Wisconsin. We have PaleoBioDB, also a really important database for all the fossil records that are kept. We even have a protein database, and you say, well, that doesn't sound like deep time, but it turns out proteins evolve. And so we're hoping to be able to put at least approximate relative ages on the protein structures. So these are all the things we build on. Now, so we use these in various ways, and I want to tell you about the first one. This is mineral evolution, the idea that minerals have changed over time. So what do we mean by mineral evolution? The first is just the change in the number of different mineral species on Earth at any one time. But also it's the diversity of those minerals and the distribution. It also has to do with the elemental composition, trace elements, minor elements. Those change through time in systematic ways as well. And the sizes and shapes. By the way, for those of you outside, there are a bunch of seats down here. Please come in. Don't hesitate. So the thing about sizes and shapes of minerals is, to me, I started collecting when I was maybe 8 or 9 years old. I love minerals. They're fascinating. They're so diverse. You know, scientists don't talk about why some crystals are long and thin, some are short and fat, and different colors and so forth. That's not the main study in mineralogy these days, but it's telling us something about Earth history. It's information, and I think that's important as well. So we focus on the upper 3 kilometers of Earth's surface because that's what we can mine easily. That's what we can see on other planets. That's also where you're going to have interactions with biology. So these are very important aspects. But you could also think about mineral evolution much deeper in the Earth if you wanted to. And the basic idea is that new minerals form through a combination of physical, chemical, and most surprisingly, biological phenomena. I have to do an aside. There have been any number of biologists who have criticized this program. They said, you can't use the word evolution. That's our word. That's not your word. And I have to respond to that criticism, that complaint. For one thing, we've used the word evolution for over 100 years in geology. The evolution of the igneous rocks. People talk about evolution of meteorites, the evolution of planets. This is nothing new. But evolution in this context means something more. It means complexification through time. That is the idea that you go from a simpler system to a more patterned, a more complex, more varieties of minerals and so forth. Also congruency. Congruency means that each stage of the evolutionary process logically follows from the one that came before. And so this isn't just a bunch of random things. This is a logical sequence. But it's not this. And I want you to erase this from your mind. It's not natural selection. So we'll get rid of that. Okay. To give you a sense of why, when this was introduced, this idea was introduced in a paper in November of 2008, so just 9 years ago. And when it came out, it really caused a little bit of a stir. And one of the reasons is that this question was embedded in that paper, and I don't think it had ever been asked before. Now think about that. That's a surprise to me. It's a cultural, it's a sociological surprise, because almost every science you talk about the first, the origin, where things began. And yet in mineralogy, the question of what was the first crystal in the cosmos, I don't think had been really formally addressed. And you think about that. 13.8 billion years ago, we were told there was the Big Bang. And everything came into existence at that point in time, and it was incredibly hot, and it was incredibly dense, and there weren't even any atoms at the beginning, and so there certainly were no crystals. And then these expanded and cooled, but the very first atoms that formed after the Big Bang were primarily hydrogen and helium. They're gases. You're not going to form crystals from those gas elements, so there were no crystals then. So when was the first crystal? And you say, well, the gases formed stars. And large stars, and they began to go through fusion processes, creating more elemental richness. And so, but stars are too hot to have crystals, aren't they? And so you think about it. So I want to give you a hint. Supernovas, these are exploding stars. So there they are exploding in front of you, boom. And what happens is when the stars expand and the gases move outward, they get cooler. And those cooling gases then can, under the right circumstances, precipitate the first crystals. So guess what that first crystal is. It has to be at a low enough temperature the crystal will form, and it has to be formed of an element that's abundant in stars. What do stars make? Any guesses? Iron. Some of you know. That's a very good guess, yeah. Iron was certainly an abundant element, but it's not the one. It's diamond! Diamond, I mean, this is so cool. The first mineral in the cosmos was diamond. And the reason is because carbon is abundant in stars, especially in the envelopes as stars expand and lose their material. And diamond crystallizes at 4,400 Kelvin, which is extremely high temperature, the highest temperature for any of these minerals. Now, if you cool down a little bit more, you get to graphite, because graphite's the more stable form of carbon. But these vapor-deposited crystals were the first. And what we think is that after diamond and graphite, there are about a dozen or so of these early crystals that formed in the envelopes in the gas from expanding stars. And these litter the galaxies in dust and gas particles. They still fall to Earth today as pre-solar grains. And they contain about a dozen what we call the minerals. That is the beginning, the founding, the basis of all future mineralogy. Now, if you look at these minerals, there's carbon. That was abundant. So was silicon. There's titanium and nitrogen and a few others. 10 different essential elements in all, abundant in stars, forming the minerals. And so the question becomes, how do you go from 12 different mineral species with only 10 essential elements to what we see today, which is 5,300 mineral species with over 72 essential elements in those crystals? And it's that question that really drives all of mineral evolution. So let me tell you a story. Here's the nebula, a distant cloud of dust and gas. The sun would be forming in an area much smaller than represented by this dot, but a tiny part of this nebula. And what you have then is you have the early nebula, where a perturbation brings that dust and gas into a swirling mass. It starts rotating on itself, it starts collecting, and 99% of the mass goes into the central sun. And that sun begins to send out flashes of heat. And around that are the scattered gas and dust. Now, the dust cannot really accumulate at first by gravity. The individual dust particles are too small, but they collect by electrostatic forces. And just like in the corner of your bedroom, there are dust bunnies in this early nebula. And those dust bunnies then are just floating around, and then they're flash heating events. A little bit enigmatic. Some of them may come from that proto-sun sending out pulses of heat. Others may be nebular lightning. But in any case, what you do is you create these little droplets called chondrules, just a millimeter across. And the chondrules then refine those elements, and you now find that there are about 60 mineral species found. They fall to Earth even today in those primitive chondrite meteorites. Many of them are, as I said, 4.567 billion years ago. And those mineral species, about 60 of them, half of them are microscopic that you can barely see. You need special equipment. Now, the chondrules came together. They clumped into larger and larger groups, eventually 100 kilometers, 200 kilometers, 300 kilometers, planetesimals that melted and differentiated. So you form a metal core, you form a silicate mantle. There were new processes, aqueous alteration, thermal alteration, shock impacts that formed new sets of minerals. And so here you can get up to about 250 different mineral species. So we've gone from 12 to 60 to 250. That's the starting point of planets and moons. Then you start forming much larger planets. And when you get a planet-sized object, you can start doing new things. You have, especially if you have volatiles, you have fluid-rock interactions of new sorts. Now, we call this very first stage of planet formation the black Earth, because you're covered by a black basaltic crust. And this is true for every object in our solar system in the inner terrestrial planet realm. That's Mars and Venus and Mercury and Earth. Now, if you have a dry world like the moon or Mercury, we think this sort of cuts off mineral abundances, diversity, to about 300 species maximum. We think this is the end point. If you have a wet world, then you can start forming many other kinds of minerals, clay minerals, hydroxides, even ices when it cools enough to have ice forming at the poles. And so this gets you up to about 420 minerals, we think. We think this may be the end point of Mars. Earth has other tricks up its sleeve. Stage 4 of mineral evolution is when you have heat coming from below. That basaltic layer on the outside then partially melts, and especially if there's water involved, you start remobilizing elements. You form new kinds of magma called granite. The granite rises to the top because it's less dense. And in the late stages of granite formation, you concentrate all sorts of interesting chemical elements like boron and lithium, beryllium, tantalum, and cesium. These form special minerals. Now, the oldest of these complex pegmatites that show these 500 new kinds of mineral species is about 2.7 billion years. And we wonder, did it take that long for Earth to process the near-surface environment to create these new minerals? In any case, stage 4 takes us up to about 1,000 different mineral species. And we think they're probably younger than 3 billion years. Another very important mineral-forming aspect of Earth that doesn't occur on any other planet in our solar system is plate tectonics. Because with plate tectonics, you subduct huge slabs of the crust. This is wet material that plunges down all the way into the upper mantle, and you rework large volumes of the crust and mantle, selecting and concentrating elements. Then they come to the surface in volcanism. So what you have is new modes of volcanism. You have massive sulfide deposits with new sulfate and sulfide and sulfur salt minerals. And then you have high-pressure metamorphic suites. So for the first time, the deep minerals are brought to the surface through tectonic processes. And this gets you up to about 1,500 different minerals. And so when you think about it, we're now at 1,500. Purely by physical and chemical processes. But on Earth today, we have 5,300 species. And so what's missing? And the thing that's missing is life. And it turns out that life creates more than 2/3 of all the mineral diversity we see on Earth. Most of it indirectly, as you'll see, but this is an amazing realization. Now, one of the ironies of this whole thing, I got into this business because I was interested in the origin of life, and there's many discussions about how the origin of life depends on minerals, sulfide minerals, or clay minerals, or maybe some more exotic minerals. So that's been a hypothesis out there, and minerals play many different roles. So when you think about the origin of life, and I'm not going to give you a whole lecture on that, but when you think about it, we believe the origin of life occurred through chemistry, and the chemistry is based on carbon chemistry, just like life today. So it's carbon-based. It used the raw materials that were available on Earth. That's the oceans, the atmosphere, rocks, and minerals. Those are the things you build with. And the origin of life is a sequence of steps, chemical steps, going from the simplicity of the kinds of gases that came out of volcanoes to gradual increase in complexity and organization. This is the kind of process that Earth-like planets can do in all sorts of ways. So minerals could play many roles. They could protect those molecules in cavities and pockets on the surface. So that's one key idea. They could act as catalysts, forming new, more efficient reactions that mimic the kind of biological reactions we see on Earth today. They can act as scaffolds, assembling smaller pieces into larger building blocks. And minerals have been shown in laboratory experiments to do this. And they can select and concentrate the molecules from the very dilute prebiotic soup. The ocean was no place to form life, at least the open ocean, because it's a vast volume with just a few molecules that rarely bump into each other. But at surfaces, especially mineral surface, you select, you concentrate, you can organize those molecules. So these are all ideas that are out there that minerals play key roles. But what I find is a delightful turnaround is that mineral evolution depends on life. Life depends on minerals depend on life, hence the coevolution of the geosphere and biosphere. The next stage, the very most primitive microbes, basically exploited the chemical imbalances at Earth's surface as magmas and other rocks came to the surface, and you had chemical reactions that would have happened anyway, minerals that would have formed anyway, but they form in layers, they form in different kinds of arrangements simply because the microbes exploit that. They catalyze the reactions, and in the process, they take that chemical energy and use it to survive. But the game changer, the thing that led to the maximum diversification, was stage 7, and that's the rise of oxygenic photosynthesis. And here we see how microbes producing an oxygen-rich atmosphere then affects the entire near-surface environment. Essentially, the surface rusts. All of the minerals that were present were now exposed to this new, very reactive chemical oxygen. And so you form oxides and hydroxides by the thousand. Microbes did this. We see, there we go, I'm sorry. So here is this rise of photosynthesis. And we call this the red earth phase because essentially we form a lot of iron oxides and other oxides at the surface. And it really is red. If you go to Carnegie National Park as one example, there are entire canyons composed of these red iron oxides. They're quite spectacular. You see the largest iron mine in Australia, the Tom Price mine, and huge volumes of iron-rich rock. Very, very rich ore comes out of that. So we have this hypothesis that we've been floating and trying to study, that 2/3 of all the mineral diversity on Earth comes as a result of microbes. Microbes creating oxygen and photosynthesis. And that changed things. Not immediately, not within the first million or 100 million or 200 million years, but gradually over the next several hundred million years, we see the rise of new minerals. Most of the minerals of copper could not have formed before the great oxygenation event. So when you go to museums, many of my favorite minerals are these blue and green copper minerals. This is the consequence of oxygen. Most of the uranium minerals, most of the manganese minerals, nickel, iron, molybdenum, go down the list. Any element that's sensitive to the oxidation state will suddenly have a whole new range of possibilities for new minerals. And that's what we see on Earth's surface today. And many of the most colorful minerals as well. So this is a time when Earth became much more colorful in terms of its mineral kingdom. So this changed roughly 2.5 billion years ago, and continuing for several hundred million years, we think is the single largest effect. Now, there are other stages as well. Stage 8 is about a billion-year period when the oceans gradually from the surface to the very depths became more oxygenated. It's been called the boring billion because it seems like in many ways there weren't a whole lot of biological changes, maybe not a lot of mineralogical changes, but it wasn't boring at all in detail, and entire books are now being written about this billion-year period. And then we had a period when Earth went through a series of radical climate fluctuations where it became extremely cold, and as it got cold, ice started covering the poles and moved farther and farther south. That reflected more sunlight, which means Earth got even colder and reflected more sunlight, and this is a feedback effect that led to global glaciation. We see this global glaciation even in equatorial regions of Africa where rocks which form right near the equator show unmistakable signs of glacial activity. So this is astonishing. We can think of this period where not a lot of new minerals formed. We call it white Earth, and the dominant mineral on Earth's surface was ice. Ice having a crystal structure and a composition H2O. So that's white Earth, but that didn't last forever. After a few fluctuations through hothouse and snowball and hothouse again, we came into the modern era, the stage 10. This is the period when life emerged onto land, where we see many, many new species form because of activities at the surface. We call this the green Earth phase. It's the one that's familiar. When we talk about an Earth-like planet, most of us think of this, although this is only 8% of the history of our planet. The previous 92%, Earth looked quite different. So there's new kinds of mineralization. Life learns how to form its own mineral skeletons, teeth, and bones. We also see astonishing use of minerals in new ways. I love trilobites. I have a large collection, most of which is now at the Smithsonian. And when you look at these eye facets of trilobites, each of those eye facets is a single crystal of the mineral calcite. So calcite is a common calcium carbonate. It's what makes most shell material. But these crystals are special because they need to be good optical focusers. The C-axis of the crystals are aligned and looking right at you. Now, but the problem is calcite does not make a very great lens because it has what's called chromatic aberration. The red light and the blue light bend differently. So all the colors would be blurred for a trilobite. But when you look in detail at these lenses, they're not just pure calcite. They have a gradation from the center to the edge in the ratio of calcium to magnesium, such that chromatic aberration is exactly corrected. So that's evolution for you. That's what evolution can do in the trilobite eye. One of the big mineralizing aspects of our modern terrestrial biosphere are root systems. Root systems first appeared in the fossil record just as little 1 centimeter things about 410 million years ago in a chert in Scotland. But in subsequent time periods, you find the roots get deeper, the plants get taller, the plants get taller, and the roots get deeper, and very, very quickly you have root systems like the ones we see today. And this had profound effect on the near-surface environment of our planet. It did things like producing vast quantities of clay minerals that had never been produced before. It armored the banks of rivers, so rivers could no longer just easily meander, but rather they had root systems holding them in place. It caused the seeding of clouds, fungi, this new kinds of fungi that interacted with root systems themselves, new kinds of soil microbes, and of course things like worms, the subsurface soil. So a whole new biosphere created by this interaction between life and the terrestrial surface environment. That's pretty profound. So my conclusion, and this is the basic conclusion of mineral evolution, is that Earth has changed dramatically over its 4.567 billion years, and that many of those changes can be tied to this co-evolving geosphere and biosphere. I just told you a story. And the story is a nice story. I think it's a story that can be used to teach about Earth science. It's a story that can be used in museums to illustrate Earth history. But taking a step back from this, it's not entirely satisfying because it's a very qualitative story. There's not a lot of numbers here. There's not a lot of specifics. It's just sort of a general, this happened and then that happened, almost a just so story. And scientists don't really like that. They want to feel like there's something more rigorous and quantitative. And so I want to tell you what we're doing to try to turn this idea, which was very qualitative in November of 2008 when we started, into something that has a much more quantitative, rigorous grounding. And the way we do that is data-driven discovery, using large data resources to really quantify the kinds of changes that occurred during Earth history. So I want to take you through some examples that are really inspiring us today to think about Earth in a new way. So the first thing I want to do is look at these large and growing databases. We're going to look at two parts of it. One is the mineral evolution, and the other is the network analysis. So in terms of mineral evolution, we've been focusing primarily on the first row transition elements. These are 9 elements of the periodic table that are very abundant in Earth's crust. They are very sensitive, most of them, to the behavior of oxygen in the atmosphere, so they give us hints about this oxygenation. And they play very important roles in biology. So for these reasons, we focused on elements. And what we've done is in our database, we now have 60,000 data points in which we have an age, a mineral, and a locality for these different 9 elements. And we can plot them in various ways. And when you see a plot through time, and these, you're going to see several plots that sort of look like this. On the vertical scale are just the number of mineral locality pairs that fit into a particular age bin, in this case a 50 million year age bin. And on the horizontal scale is time present 1 billion, 2 billion, 3 billion, 4 billion years ago. You see the data get a little bit sparser as you go farther back. But you also see a couple of very important points. One is there's kind of pulses of mineralogy. It's not a completely uniform sort of thing. And we think that the pulses are largely due to the fact that Earth has gone through some really big tectonic cycles called the supercontinent cycle. There are times in Earth's history when the continents are more dispersed, as they are today. And there are times when the continents seem to have come together, as they did, for example, in the formation of Pangaea, perhaps 250, 300 million years ago. So when you look at a diagram like this, you see the Earth scientist's view of these continents moving over time. You see the formation of Pangaea, and then you'll see eventually after the continents are sort of together, then they break apart. This is a sped up diagram showing you about 500 million years of Earth history. And the thing that's interesting is that there are pulses of mineralization. Now these pulses have been known for some time because there is a wonderful mineral record of Earth history called zircon. Zircon, sometimes used as a gemstone, is a zirconium silicate. It's very, very hard. It's very resistant. It's formed in many kinds of rocks. And when those rocks weather away, tiny crystals of zircon are deposited as part of the sand. Every beach you've ever gone to has zircon crystals. Every sandstone you've ever seen has zircon crystals. And you can extract those crystals and study them one by one. This has become a real industry in geology, where some laboratories can measure 100 zircon crystals per day and give you ages on those crystals because they contain uranium. And uranium is like a ticking clock. Gives you those radiometric dates. And so here's a graph, one of many, many in the literature, showing the pulses of zircon. And even though you can't see all the numbers, you basically see 5 pulses. Those are 5 episodes of supercontinent formation, which are seen through the last 3 billion years of Earth history. And what you see here then is the data I just showed you before, those various transition elements. And again, you see the pulses. Each pulse, shown by the vertical red bar, the maximum for a billion-year interval is found underneath one of those pulses. We see Kennerland, 2.7 billion years old. We see Nuna, about 1.9. Rodinia, a very enigmatic supercontinent we're trying to understand because there's not as much mineralization as you see in other time frames, although there's a big pulse of zircons there. And then the more recent two. And so that's one thing that's causing the variation of mineral diversity through time. It's the supercontinent cycle. But on top of that, we see a biological signature. And nowhere do we see this more interestingly than in the element manganese. Manganese occurs in a more reduced form called manganese 2+. It forms many beautiful minerals like rhodochrosite. It also forms in a more oxidized form, manganese 4+, shown here with also some pretty cool minerals, but not quite the same as rhodochrosite. And Dan Hummer has built a mineral database of the ages of manganese minerals, and he's colored this database according to the different oxidation states. In red, you see manganese 2+, in purple, you see manganese 4+. And what's very clear is that the purple is much more a higher fraction towards the last 500 million years when life really started playing a role. These are near-surface minerals that form as part of the terrestrial biosphere. So here we see a direct link between mineralogy and the formation of minerals and the biosphere. This is the kind of thing we're studying. We sort of look at all these different minerals. Here's the 9 different transition elements, each one shown one after another in what's called a skyline diagram. And there's a huge amount of information here, quantitative information about how Earth has changed in its near-surface environment over the last 3 billion years. So that's the kinds of things we're doing with mineral evolution. We can now do these little plots for every single of those, one of those 72 mineral-forming elements. We can pull, this is a diagram which I can send to any of you who are interested, and you can pull out each of these as a PDF high-resolution file that you can look at and see, for example, how lithium changes through time, or molybdenum, or whatever your favorite element might be. You can see that. Okay, so that's fun, and this certainly is a quantitative approach. I think that mineral evolution is advancing because of that mineral evolution database. But the really fun thing, and the brand new thing, something that's, our first mineral network diagrams were only produced about a year ago, and the first paper only came out last August. This is a new way of looking at mineral systems, and I want to bring you into this world because as a mineralogist, seeing the natural world in a new schematic way is really exciting. So this is mineral network analysis. The idea is you can build a network, and it's very much like a social network. This, in fact, is the research network of people in my group that are working on networks. And you can see who's connected to who and who publishes with whom, and there's some outlier people who aren't as central to the effort, and other people who are sort of involved in everything. This is the paper that just came out, Shauna Morrison, the first author, but half of these individuals are data scientists and half of them are earth scientists. So this is the kind of collaboration that's essential. And what we do is we basically, let's build a network. And in that network, the nodes will represent individual mineral species. The links represent 2 minerals that coexist at the same place. And then you build a network with lots of minerals and lots of localities that give you information of this sort. So think about your granite countertop. If you have a polished piece of granite someplace in your home, where you certainly can see them on campus and all sorts of places, just the stones in the lobby. And you basically see a rock. It's a combination of several different minerals that coexist. That's a clique in the terminology of networks. And so you basically can go into old books. You can find different rocks described. It'll give you the list of all the minerals that occur in those rocks. There are tables of thousands of different rocks. We build those tables, often just typing them out by hand. In this case, there are 729 different kinds of rocks. There are 51 different minerals. It's a big matrix. It's a big spreadsheet. So you see what coexists, and you can make from this a simple network. This is the very first network we ever produced, 37 minerals that occur in what are called igneous rocks, things like granites and basalt. And lo and behold, you look at this, there's granite, there's basalt, there's a rock called nepheline syenite. And in a diagram like this, a simple diagram with 37 nodes, the entire field of igneous petrology is represented schematically. You know, when I took igneous petrology, you had a thick textbook and you learned about all the different rock types one after another. And that's important. But it's so neat to be able to visualize the whole things and see how those different rock types interact with each other. So this is a way of visualizing data, which otherwise is very, very difficult. It's hard to imagine 37 minerals all at the same time. Here now is another representation of a larger data set with 51 igneous minerals. And it's what's called a multidimensional scaling diagram. Two minerals that are commonly associated with each other, like quartz and topaz, are close together. Two minerals that are never associated, like quartz and nepheline, are far apart. You can basically show this diagram to them in 3 dimensions, and you can look at different relationships with this. And the thing that's amazing about this diagram, again, this is telling us a huge amount about things that we have already learned in igneous petrology. Let's look at this diagram again in 2 dimensions, because what I want to do is show you how information is embedded in this diagram. A very common and one of the first things you learn in igneous petrology is as you cool a magma from high temperature to low temperature, you go through something called the Bowen reaction series. And there's 3 parts. There's a plagioclase trend going from calcium to sodium-rich minerals. There's a mafic trend of iron and magnesium minerals, and there's a late-stage trend. This is extremely well known as a sequence, an evolutionary sequence that goes through igneous rocks. And here's that diagram. There's the plagioclase trend, there's the mafic trend, there's the late-stage trend. In fact, all of Bowen's reaction series is embedded in this diagram. And many, many other phase relations as well, the things that igneous petrologists have studied. It's all here, and it's in very high-dimensional space. You're seeing a 2-dimensional projection. But with 51 minerals, this is essentially 50-dimensional space that we're probing and we can explore using various kinds of analytics. I want to introduce one other kind of network diagram called force-directed diagrams. What you're seeing here is a bunch of minerals again, 51 minerals from igneous rocks, so we're using the same data set, but represented in a different way. In this case, there's essentially a spring between any 2 minerals that are related. The spring will be very short and tight if the minerals occur together all the time. The spring will be very long and loose if the minerals rarely occur together. And so you can basically look at this as an equilibrium diagram. All the springs are kind of stretched or compressed into a stable assembly. And then you can color them in various ways. In this case, the size of these circles represents how common the mineral is. The spacing is how frequently they occur. And then you color them according to various sort of mineralogical criteria, anything you want to use. And so you can basically take this diagram and then you can manipulate it. You can do this on our website, dtdi.carnegiescience.edu, and you can do this yourself. You can touch any one of the nodes and you can see how they move. There's magnetite, for example. Magnetite's interesting because it's connected to every other node. That means that this is a very centralized net, a very dense net, and also the degree of separation from any mineral to any other mineral is only 2. You can always go through magnetite to get to the next. These are the kinds of network metrics we think about. Now we can apply this to every planet and moon. Here you're looking at Earth, the moon, the asteroid Vesta, and we know a lot about Vesta because of what are called HED meteorites, and Mars, which we're now studying. And it turns out that these networks have interesting similarities, but also some important differences. In fact, Earth's network is quite different from any of these other worlds, and we think that may be a biosignature in and of itself. The distribution of minerals on Earth has its own distinct pattern, and we're exploring that as a hypothesis that perhaps Earth's life creates a very distinctive distribution. Let's look at a couple more networks. This one's for copper minerals, the 243 most abundant copper minerals, which are really important in Utah. They're being mined very close to here. And what you see in this case is node Size, again, corresponds to how abundant or rare the particular mineral is. And the colors, in this case, have a compositional framework. So in red, we've got what are called sulfide minerals. Those are minerals in which they have sulfur but no oxygen. In blue are minerals that have oxygen but no sulfur. Those are oxides and carbonates and things like malachite, which is one of my favorite minerals. And in orange are things that have both sulfur and oxygen. They're called sulfate minerals. And you see this high segregation, something we never suspected before. We never saw that. And you don't see it necessarily in other types of mineral groups, the same kind of compositional separation. So these are the kinds of things we learn. When we do this manipulation, we find that the most abundant mineral, the largest circle, is chalcopyrite, connected to almost every other node, not quite. So the diameter of this, the degree of separation is 3 on this. There's malachite, also connected to almost everything else. And that's not surprising. What really surprised us was the next find, that big green circle, that's native copper, pure copper metal, which is found as a mineral many places on Earth. And it's connected almost entirely to the lower half of this graph. That's to the oxides and the sulfates. It's not connected to the sulfides. And for a mineralogist, at least for me, that was a real surprise, and we're still trying to understand what that is telling us about the genesis of copper ore deposits. And then we can look at this in 3 dimensions. Here's the manganese data that Dan Hummer, I showed you his work earlier. And Dan looked at this and he said, wow, when we make a network of manganese minerals, you see these big central hairy ball of stuff. And then you've got a little clump up here and you've got a little clump down there. The clump up there is what are called, remember I told you about pegmatites, those minerals, rare minerals that form with granites? Well, these are manganese phosphate minerals that form in pegmatites, very rare minerals, and almost all of them 2+. So you see a big red circle there with lots of red manganese 2+ minerals. The little clump off to the right side is manganese metamorphic minerals, where the manganese minerals have been subjected to high temperature and high pressure, and those are also dominantly manganese 2+ minerals. But then you see the big clump in the middle, which tells us that's where most of the near surface, the biologically mediated manganese minerals are, and they're rather distinct from the pegmatites and the metamorphic minerals. And we can look at this in these different kinds of minerals, and we can rotate this in 3 dimensions. And in fact, this is really cool. You can zoom in and zoom out. You can also do this with virtual reality glasses. So that means you can be walking through this network, and with the right tools, you can touch on the different nodes and find out what it is and pull it and see how it's connected and really explore this deeply into this inner working and find out what these different minerals are doing. So this is really an astonishing new way. Now, I just want you to step back and imagine that you have been a scientist through your entire life, for 30 or 40 years. You've studied manganese minerals. This is your field. In spite of that, there's no way that you can keep 500 manganese minerals and how they connect to all the other 500 manganese minerals, not to mention the other thousands of minerals that are out there. You just can't keep that in your mind, and no matter how much you study, you'll know certain associations well, but the richness of data that's present here, the amount of information that's present in a single rendering, and then you can manipulate it and play with it. You can touch the different nodes. You can learn all the metadata about the localities, about the different properties. You can find all that information embedded in a single graphic. This will transform the way mineralogists think about their world. I want to tell you one more thing about networks, and I'm going to move now to fossils, because I think it's a little more transparent to see how this works. Fossils are an evolving system. And so we're very interested in studying fossils of various periods. This work is led primarily by Drew Macente at Harvard University, working with Andy Knoll, and we're interested in a period called the Ediacaran. First, let me just give you an overview. Here's a graph of the last 540 million years of all the animal families on Earth. And what you see are blue dots, each representing a family of animals. And you see connections when 2 families coexist in the same rock, the same bed. And what you're looking at now is a sweep of 500 million years where in blue, in that left-hand part, are early Cambrian fauna. And then you see what's called the main Paleozoic fauna in red, and then more modern fauna in black. The remarkable thing about this diagram is the only information is two coexisting families. That's the only thing that you see, and you'd make the links and you build the network that way. But what's very clear in here, there's a timeline running through this. What you find is going from the early Cambrian period to the modern period, and a network of an evolving system has to show you a timeline, because things that occur early on only exist with themselves, and the things at the end of the timeline only exist with themselves. And so you're going to see a line like this. What is so amazing, this embeds other kinds of information. For example, some of the major mass extinctions in the history of Earth. There's no information here about mass extinctions that just falls out of the network. So you can discover things from networks that you don't put into them, just the coexistence. And the reason this has been fun is we've just built a data set of about 100 localities and about 100 genera of what are called Ediacaran fauna. These are very enigmatic animals that lived before what was called that Cambrian explosion, the period just before what I showed you there. And when you look at these, it turns out there's a timeline. There's something called the Avalonian fauna, which comes from about 575 to 560 million years. And then there's the White Sea fauna from 560 to 550, and the Nama. And there's been a big debate in the rather small Ediacaran paleontological community about whether this represents near shore or offshore, shallow water, deep water changes in fauna, or whether this is some kind of more extreme event. So we built the network, and see if you can find the mass extinction. There's the network. There's that Avalonian. Yellow is the White Sea. Red is Nama. The blue is species that coexist in both the Nama and the White Sea, but not in the Avalonian. And I think you can see that there's a pinch point in here. So there is at least a faunal turnover. There's a major event right there at 560 million years. It may be the oldest mass extinction that we can record in the fossil record, and one that hasn't really been recognized before. But with a network, the fact that something really dramatic is happening there is underscored, whereas there's not a big change between the White Sea and the Nama faunas. So that's the kind of power that we see. And I'm going to show you one more thing. This is a crazy network, but I just showed you that when you have an evolving system, there's a time axis through it. Now, what we'd really like to know is what is the time evolution of proteins on Earth? There are more deeply rooted ancient proteins, there are modern proteins that just evolved in the last few million years, everything in between. And what this diagram that Jana Bromberg put together at Rutgers University shows is 6,000 protein structures. Each point represents a structure of a protein, a group of atoms. And if two structures are very similar, like your two hands that fit almost exactly together, those 2 points occur close together. And if two structures are very different, they occur far apart. And there are metrics of measuring how close or similar or different two proteins are. Then the lines represent proteins that do the exact same chemical job in an organism. And what she found after she made that network, which was not colored at first, she said, now I'm going to color this network according to what transition element, first row transition element, is dominant. In red is iron. In blue is manganese. In yellow is copper. And it turns out that's the exact sequence that you'd expect in a world that goes from an anoxic environment before the Great Oxidation Event to an oxic environment after the Great Oxidation Event, when you have lots of copper, but the iron has all been deposited out in those great red deposits. So when you don't have as much iron and you have a lot more copper, you're going to change. There's a time axis in this diagram as well. And that's astonishing because certainly when you do protein structure work, you have no idea what the age of the individual proteins are. There's a lot more subtlety to this, and she's working on this very hard at higher dimensional space to figure out subtleties, but this is a really exciting direction. Finally, one last thing that we can do, because one of the things mineralogists have never been able to do is make predictions where to go to find new minerals, what minerals are missing. And it turns out we can use the exact same data sets I've just shown you in a way that's very familiar to you. It's called market basket analysis or affinity analysis. And you've all experienced this because you go to Amazon, you buy a book I tried to buy Jonathan Lenine's astrobiology book, but it was completely out of print, and the cheapest copy was $300, so I didn't buy it. But they immediately, within a second or two, sent me this and said, you'll probably like these books as well. And I can't imagine why. I mean, why John Horgan's End of War, I don't know. But they seem to think that that would be something that would appeal to me. So this is something that you've all experienced. This is market basket analysis. And it turns out that you can do the exact same thing with minerals. Because some minerals like to be with each other, some minerals hate to be with each other. You have different localities with different properties. And it's just like surveying hundreds of millions of people and the billions of books that they buy and seeing who likes what and what kind of gets distributed where, all that geographic information, all the individual information. So if you can find groups of minerals that are similar and like each other or dislike each other, you can apply the same mathematics. And so here's what I imagine the future of mineralogy. This is what's going to happen. I don't know how soon, but it's going to happen. You can put on your virtual reality glasses. You go into the network of minerals. You find one of your favorite minerals, Gillespite, something I worked on when I was very young, and so I really like this mineral. And I say, wow, I want to see pictures of specimens of Gillespite. I want to see localities where Gillespite occurs. And as you use your glasses and you push on that Gillespite node, you'll see all this information. What are the other minerals that occur with Gillespite? What do they look like? What are the localities? And then you ask the computer, where can I go in the world to find Gillespite where it's never been found before? And the computer will tell you. Let's say there's a 75% probability if you go to this locality, you will find a previously unreported deposit of Gillespite. Or perhaps you will find that next billion-dollar copper mine. And the U.S. Geological Survey is working with us on exactly this problem. This is the future. I don't know how soon it's going to happen, but it's inevitable. This has to happen. It's going to take time. It's going to take resources. It's going to take a lot of creativity, money, which we're trying to raise. This is the future of mineralogy. And so I hope that I convinced you that when you look at Earth, you're looking at a planet of change. It's changing still today, but it's been changing for billions of years. That when you see that change, you're seeing the signature both of geology and biology, and that data-driven discovery is going to play a huge role in our future understanding of our planet and our home. With that, I thank you very much for your attention and hope there might be time for a few questions. So the age of the Earth is estimated by the most primitive meteorites that have been found. That's the building blocks that clearly formed before any planets or moons. And the most ancient part of those ancient meteorites, little inclusions, little round droplets that formed, are dated at 4.567 billion years by using the various radiometric techniques. For example, the uranium isotopes and how they have changed like a ticking clock through time.
This has just been terrific. My question is, did you bring your trumpet?
Did I bring my trumpet? No, sadly about a year ago, I'm traveling so much with this exciting new science that I no longer play professionally. I did my last concert about a year ago, but my wife's a violist and I'm also a cellist, so we play string quartets. But just in the privacy of our own home, you'll never be subjected to that.
So you mentioned the data science. This is very fancy topic for now, but how do you collect the data for the million years ago?
Oh yes, so how do you collect the data? And of course, this is done in a variety of ways. Brute force is one way, where you get undergraduates to read papers and type line by line. But there are also some very exciting new machine learning techniques where we have access now to many millions of individual papers presented as PDF files. And using techniques like deep dive and snorkel, where you can go in, the machine looks for the data that you're interested in, for age data, there's certain keywords you can find that indicate there's data, and then it comes back with a table based on what it read. And then you look at the table, you correct it, you train the machine, say, no, this was wrong, but you got it right here. The machine goes back and you train it again. And you do this for a few iterations and the machine can do that. So we've begun to do machine learning retrieval of data from many millions of PDFs. We've done that with the cobalt data, which we did absolutely rigorously brute force, and then we did it with machine learning, and we have an 85% overlap in our two databases. So it looks like it's a very promising technique to build these data resources much more rapidly.
So can you use mineralogy to determine whether life once existed on Mars, once you've studied it on Earth?
We really hope to be able to use Mars mineralogy. So I'm on the Curiosity team, and several members that I work with are thinking about exactly this process. There's no one mineral species we think is a smoking gun for life, but it's the distribution, it's the characteristics, it's the minor elements, and perhaps as we explore more and more of the planet, we'll find that distribution of rare minerals, which on Earth at least looks like a biosignature. But we're still in the early days of this for Mars, and this is high on our minds. This is very much something we want to know. We want to know if Mars was once alive, or perhaps if it's still alive today.
Do we know if have all minerals evolved on Earth, or is new mineral evolution possibly going on?
Oh, new mineral evolution, absolutely. In fact, this last year, our group published a paper on stage 11 of mineral evolution, which is human-generated minerals. That human activities have produced hundreds of minerals just inadvertently by digging mines and putting ore on the surface and making mine tunnels, by having artifacts. In ancient shipwrecks, you find all sorts of new minerals. In ancient Roman cement, there are minerals that never have existed on Earth before. And then, of course, we purposefully synthesize many things. Laser crystals, semiconductors, all kinds of new metal alloys. These are all mineral-like materials. They're not approved by the International Association because they're human-made, but there, in fact, are thousands of new mineral-like materials on Earth's surface, which are going to mark our time in the sedimentary record of our cities, of our roads, of our infrastructure. They will mark our time as different from any other time in geological history. And if you can imagine coming back in 100 million years in a future Grand Canyon that slices through one of our cities of today, you will see in that bed a very distinctive marker that shows that we have another stage of mineral evolution. There's a gentleman back here. Yes.
Do you see causality there?
Causality is such a great word. When you start doing big data, they say don't talk about causality, talk about correlation. And so I'll be a little careful, but we do think that there is actually a causal relationship, because when your two continents come together, you can imagine these are land masses, and if like the formation of the Himalayas today, you form a higher and higher mountain range. There's all sorts of stresses, there's fluids circulating. This is where many ore deposits form and new minerals form in that environment. And also, because you're making a mountain range, you're more likely to preserve those rocks and minerals for later time. So we think when we look at the zircon record, we're seeing primarily episodic formation of minerals, but we're also seeing perhaps a bias based on preservation, where other times when continents are splitting apart and sediments are becoming more deeply buried in basins, perhaps we're losing a higher fraction of minerals from those times.
So as an electrochemist, you could look at a protein as they're carrying around a remnant of a battery.
Yes.
An iron, a manganese, cobalt. And with that timeline, it would look as though our oldest single cellulars were very dominant with the iron. And presumably the manganese starts coming in when we get into things like photosystem tubes and such as that. Yeah. So do we find much manganese on Mars, or are we always going to have a very old biological life form?
Yes, indeed, on Mars we certainly see manganese, we see trace amounts of copper. I mean, all these first row transition elements that form an important part of Earth are on Mars. Now, what we're not so clear on is whether they're the very dynamic fluid rock interactions that cause the reworking, the formation of ore deposits on Earth. We may not get the concentration mechanisms on Mars. The one place where we might, and I think that we should go and look, but we haven't, when you have a very large impact, you know those huge craters that you see on Mars, that impacts a huge amount of energy to the surface. And it means that there are going to be hot rocks and fracture zones around the edges of the meteorite. And on Earth, for example, in Australia, some of the biggest ore mines are in these hydrothermal, as they're called, hot water zones of circulation that occur at the edges of a large impact zone. So I think those are the places to go on Mars to look for the origin of life. But that's not where we generally plan to. They want to look for old lake beds and places where there was water in the surface environment, and I can understand that as well. But ultimately, we have to look farther than just those deposits. I'm sorry. When did water appear is a great question. How early did Earth become a blue planet? There's some people that think that water spewed out of volcanoes right after it began to form, and then one of the big disruptions very early in Earth history, perhaps in the first 50 million years, was what's called the moon-forming impact. It was sufficiently a large object, two competing planets, if you will, Earth wins, this other planetesimal called Theia lost, gets vaporized, but it becomes our moon. And then after that, you then very quickly cool the surface of Earth again. There's more volcanism spreading out. Water vapors in the atmosphere, begins to rain. And I think probably what you'd find is in the cooler equatorial regions, you start forming ponding of water fairly early, within the first 100 million years. How soon you had an ocean that spanned the entire globe is not at all clear. Some people think it's in the first 100 million years. Some people think it may have been 500 million years. But very, very early on, and about the same time we think of as life originating on Earth as well.
Wow. Thank you for this wonderful story. I'm curious, how surprised would you be if any part of it were to be changed in further discoveries?
Oh, this is a great question. So it's how surprised would I be if things were changed? I would love for things to be changed. The one disappointment I have with this whole story that I've told you is it's been accepted sort of as the truth by people around the world, including scientists. And it's not going to be real science until someone comes along and says, this is wrong, and this is wrong, and this is wrong, and this is wrong. And they challenge this, and they move the science forward so that we either have to defend our ideas or we accept that they're subtleties. Everything I've told you is certainly not exactly true. And one of the most important things that's not true is we're talking about different stages, stage 3, stage 4, stage 5. It wasn't like stage 3 happened and then stage 4 and stage 5. Stage 5 is still happening, stage 4 is still happening, stage 3 might have come after stage 4. I mean, these are things that are just settles. The number of minerals that occur during the different stages, we may find out that there are whole new mineral forming processes that we've missed. There may be something about the early Earth that we haven't recognized. The great oxidation event may, in some details, be quite wrong, and we may have new evidence for that. So I would love for other people to step in and challenge what we've reported, because I'm not wedded to the details of this story. I just think that the basic idea of change through time is fundamental, and we want to learn as much as we can about that. So if you want to jump in and publish the version 2 of the whole story, that's great. We need that.
What is the Deep Carbon Project?
Oh, the Deep Carbon Observatory. So I've been very, very lucky over the last decade or so to be working with the Alfred P. Sloan Foundation on something called the Deep Carbon Observatory. This idea arose from the studies that we were doing on the deep origin of life, and the Sloan Foundation said, that's pretty interesting. They ran these 10-year, $100 million programs and said, would you be interested in doing something on that? And I stepped back and thinking about Earth history, said, we really need to have a more fundamental understanding of carbon, because we talk about the carbon cycle, but that's the near surface cycle. That's the atmosphere, the oceans, just coal and oil right near the surface. But there's a lot more carbon in Earth, and we don't understand how the deep interior relates to the surface. We don't understand the deep biosphere, microbes that are living under the surface, which by some estimates were 50% of the biomass, but it's just it's hard to see. So the Sloan Foundation offered us the chance to begin working on this. They made me the principal investigator, and we now have an international program with about 1,000 workers, 45 countries, 150 field sites, theorists and experimentalists all over the world, over $500 million in funding right now. I mean, it's a big program. And it has another couple of years to run, and then it's over, and we're sort of thinking about what's the next big thing. I'm hoping the next big thing will be big data, because I feel like...
What is this deep?
Oh, what is deep? That's a great question. If you're a microbe, being 100 meters down is pretty deep. If you're carbon in the core, then you're talking about thousands of miles. And so deep is a term that's everything beneath the surface that really hasn't been studied enough yet. So we keep our minds kind of wide open in this realm. So for different scientists in the Deep Carbon Observatory, that word has different meanings, which I think is fine.
Last question.
So mineralogists are finding 100 new minerals every year, but it's a finite resource. How many minerals are there?
Wow, how many minerals are there altogether? We've done some estimations using big data approaches. The minimum number of missing minerals is 1,500 based on our statistics, doing something called accumulation curves. You do this in biology. You go out into a forest and you start counting birds, and people all over the world count birds. And each year you find fewer and fewer birds, but there's still a few bird species out there to be found. We're doing this with minerals, and the accumulation curve suggests that at a minimum there's 1,500 more minerals. But other modeling and making other assumptions, there could be as many as 4,000 more minerals. So it's someplace in that range. It's a few thousand. It's not 10,000. It's not 500. So we have a lot to learn about mineralogy for sure.
Well, join me in thanking Bob again.